Welcome to this lesson in which I'll give you a brief overview of machines. So I want to explain to you what a machine is, and then I'll end this video lesson with a brief description of the design project you're going to work on, which is to build a machine. So let's begin with answering this question about what is a machine. So look at this image here and look at the various objects that are shown on it. I think several of these items are familiar to you from either lying around at home or things that you see, for example, when you're outside in your neighborhood or going to school, and for example, when you cross a construction site and so on and so forth. Right? There's a lawnmower. Here's a bulldozer. You may have seen something like this. It's a handheld drill, a pencil sharpener, something that you might be using quite often. So what are all these things doing? Well, their main purpose is to make it easier to do certain tasks. For example, the lawnmower is used to cut the grass in your lawn in a way that's easier than, for example, using a scissor or a scythe. A pencil sharpener is easier to use than a blade to sharpen your pencil. So all of these things have in common that they are making life a lot easier. And so that brings us to what we can define a machine to be. So in a general sense, a machine is an apparatus that uses energy to perform work. Alternatively, you can also think of a machine as a structure that is going to transmit or modify forces that you apply to it in order to do something useful. Okay. Now, in the context of machines, you can categorize them into two types. The first one is what is known as a simple machine, and in the figure here you can see the various types of simple machines that are out there: the wedge, a pulley, an inclined plane, a screw, a wheel and an axle, and levers. So it turns out that a simple machine is one in which there are no or very few moving parts that can perform work. And as you can see from all these examples, these simple machines don't have their own energy source. So something needs to be done for them to do useful work. Right? Now it turns out that a general rule for any machine, including simple machines, is that the efficiency of a machine can never be 100%. And efficiency here is defined as the ratio of the amount of output work performed by a machine to the amount of input work done on the machine. Now remember back to our lesson on energy, where work and energy were related. Well, you can also define efficiency as the amount of energy output divided by the amount of energy input, or the amount of work done by a machine divided by the amount of energy input into a machine. Okay. Now, as I said, there are 6 types of simple machines, not 7 as I misspoke earlier. And let's look at what these 6 types of simple machines are. So on the left column here in the table is a list of the type of simple machine. So you can see there's a wedge, a wheel and axle, a lever, an inclined plane, a screw, and a pulley. And each one of them simplifies a certain type of action or actions. For example, a wedge, if you think about a scissor, you have a wedge-shaped edge on the scissor that makes it easy to cut through a piece of paper or a piece of cloth. A wheel and axle makes it easier for us to actually just go back a little bit here. The wheel and axle makes it easier for us to roll things about, which actually is easier than pushing it on a surface, because it turns out that rolling friction is smaller than, for example, sliding friction. A lever is something that helps us lift heavy objects over longer distances. The inclined plane makes it easier for us to move objects upwards. A screw is a device that transforms one type of force or motion into another. For example, a rotation motion is transformed into a linear motion here. And a pulley allows us to lift heavy objects because it helps us to redirect the force and make use of gravity in reducing the actual force we need to apply to lift a load. Okay. Now the other type of machine is the compound machine, and in the images shown here are a variety of different compound machines. So a compound machine is basically a collection of simple machines working together. Okay. Again, they may or may not have their own energy source, and they are designed so that when they work together, when the simple machines come together, they can actually provide a bigger advantage than just using a single simple machine. Okay. And let me give you one example of a compound machine. It is something that you may have used yourself, and that's a wire cutter. So shown in this image is a wire cutter. It consists of these two lever arms that are held together at a pin joint at A, and then on the other side of the pin joint are these two what one would call the cutting edges, which are basically wedges. And so this is a simple machine here in the form of a wedge, and these are simple machines here in the form of levers. Okay, so you have two simple machines that are coming together to form a compound machine. Now, as you know, when you've used a wire cutter, you actually apply a force P when you push down on the two arms of the wire cutter, and that introduces a force Q that is applied to the wire that leads to cutting it. A similar principle applies, for example, to a nut cracker. Right? Now, why is this a useful machine? The reason it is useful can be understood by trying to do this experiment if you have a wire cutter at home. Take a wire cutter and start out. Sorry, just let me go back to where we were here. Start out by trying to apply the force on the wire cutter somewhere very close to the pivot point. And you will see that as you try this experiment and you move slowly to further and further away from the pivot point till such time that you reach the position P. So let's call this distance A here, right? And let's call this distance B here. Okay? If you actually apply the force at P so that you use the full length A, you will find that it's much easier to break or cut the wire than if you applied the force at some position here, much closer to the pivot point. And that's the single most important benefit of this machine, that by using a long lever arm, you're able to apply a little bit of load and translate that into a very large force on the other side of the pivot arm, so that your wedge shaped surfaces can actually cut through your wire or break your nut. It turns out that when you study the subject that deals with this topic, which is static mechanics, you will learn about forces and moments and the principles surrounding them, and you will find that the load that appears at Q when you apply a load P on the lever arm is going to be related by this expression here, which is the ratio of B over A. Okay. So I'm sorry, so this is incorrect. This should be Q equals B. Let me just go back a little bit. It should be A. Q equals A over B times P. Right. So there is a magnification factor given by the ratio of the long length divided by the short length, and so your force Q is magnified over the force that you applied, which was P. And that's the benefit of the design here, which utilizes the levers and the wedge shaped surface. So one of the important things about a machine is that the efficiency of a machine ultimately indicates how useful this machine is, right? And what it tells us also is that how the efficiency is basically a measure of how well the energy that you input into the machine is utilized as useful work or output energy of the machine. And so this is of course a critical factor in the usefulness of a machine. Right? Now remember, in our discussion about energy, we briefly mentioned the law of conservation of energy. And what the law said is that the total energy that goes into a system must be equal to the energy used by that system. Okay, so in the case of a machine, you can think of it this way: if you put in some energy into the machine, the total energy used by the machine is going to be identical to the input energy that you put in, except that, remember, a machine does some useful work, and so some of that input energy appears as useful work, while some part of it contributes to things such as friction and heat, which are not very useful in this case. Okay? So that means your input energy is now being transformed into some useful work or useful energy, and some energy that is wasted. For example, such as friction or heat. Okay, and once you realize that, you can immediately see that the efficiency of a machine can never be 100%. So remember our original definition of the efficiency, which was the amount of work done divided by the input work or the input energy, right? And so because of the fact that you have loss of energy due to friction and heat, the output work cannot be equal to the input work, or the output energy cannot be equal to the input energy. Now, it is common to express efficiencies as a percentage, and that comes by making sure that when you take the ratio of output work by input work, you multiply it by 100 to get the efficiency in percentage value. So as an example here, let me give you two examples of machines and their efficiency. A lever is one of the most efficient simple machines. It's about 98% efficient. On the other hand, a gasoline-powered automobile is only about 15% efficient. Okay, so remember, it's the entire machine, the automobile as one machine. It's not the efficiency of the specific part of the automobile. For example, the engine. The engine is more efficient than 15%, but because of the fact that you end up losing a lot of energy to heat and friction, the ultimate efficiency of the car, which is measured by taking the amount of energy you put into the car and the amount of work it does, is only about 15%. Okay, so with that, I'm going to end by describing to you the design project you are going to work on. And this involves creating a machine that utilizes the transformation of one form of energy into another. Okay? Now remember, transforming one form of energy into another is an extremely important engineering task. The example that you might think of is taking the energy that comes from the sun and converting into electricity for your home through something like solar panels. Right? So the solar panel here is the machine that is transforming your input energy from the sun, which you can think of as kinetic energy, into electricity, which is the kinetic energy of electrons. Okay? Similarly, when you did your measurement experiments using the balloon, you expended chemical energy by blowing into this balloon and filling it up with air, and that energy got stored in the balloon in the form of the extension of its rubber material, and that is a form of elastic energy. So as I mentioned earlier, elastic energy, which is the energy due to the displacement between atoms, is a form of potential energy. Okay, so you have stored energy in the balloon in the form of potential energy, and then you tried this experiment here where you released it, and you noticed that this energy now from the balloon is expended out through the air coming out of it, and that results in the balloon moving around in a random way. Right? So that initial elastic energy or potential energy of the balloon is transformed into kinetic energy. Some of you might recognize this image here. This is from the famous series of movies called Back to the Future, in which Dr. Brown invents a machine, a fusion machine, in which you can put in any type of biodegradable material. For example, you can put a banana peel in, and it's going to convert it into useful energy. Right? And in fact, machines that are converting from one form to energy are extremely useful and form one of the great grand challenges of engineering. Okay? Now, what is your project going to be about? Well, when you release the balloon after filling it up, what you would have found is that the motion was pretty random. So the balloon moved around in all kinds of positions, right? And so that's not a very useful end result for us. And what we want to do is instead utilize that energy to make a machine that moves in a very well-defined way. Okay? And so here's what the challenge is going to be about. What you're going to do is each one of you is going to build a prototype car, and this car is going to be powered by a balloon. So here is a little cartoon schematic of a car that is made by using simple everyday material that you can find at home, and you're going to power it with the balloon. So that means the kinetic energy of the car, that is the motion of the car, is going to come from the elastic energy stored in the balloon that was a result of you blowing air into the balloon. So you're going to learn how to build the car using this link here, which takes you to a Scientific American article, and this link is also provided as a PDF file in Canvas. And then you're going to experiment with things like how fast your car can go, how far it can go, and things like that. And one of the outcomes of your project will be, of course, having a successful car. You will create a video to show all your classmates that your car is a successful machine that can actually move. And in addition to that, you're going to make a number of measurements. Okay, so to wrap up, make sure you follow through any of the URLs that are provided in this video lesson here, and you will see the design activity file with great details about what exactly is required for your activity in Canvas. So please make sure to follow up on that. Thank you.